Hi, and welcome back, everyone. In the last video, in the last class, we discussed uh, determining or calculating the probability of something happening. Now, the next thing to talk about is the probability of two or more things happening. Now, there's two ways that could happen. Two things could happen at the same time, or two things could happen one after another in sequence. In this video, we're going to talk about the probability of two or more things happening at the same time, right? And the rule we're going to develop in this video is referred to as the addition rule because it uses the mathematical operation of addition. So before we get into the addition rule, just let's look big picture. We're going to be looking at these various quantifiers, and these are the words that are bold-faced and in red. Specifically, the word not, the word or, and the word and. Okay, we've talked a little bit about the not. That's the complement, right? In this class, we're using this notation right here, the bar, right? A bar means not A. Some books, however, use a different symbol, this tilde. So if you're looking on the internet and you see that symbol, that means the same as the bar. But from here on out, in my notes, in my videos, I'm only going to be using the bar notation. Bar means not. And then we've got the two rules involved in this section, the addition and the multiplication rules, the rule for or and the rule for and. Right? Now, or is straightforward, right? If you see the word or, it's an addition rule problem. And is a little bit more tricky. Sometimes A and B means at the same time. Sometimes there's an implied then, and then A happens and then B happens. We got to be a little careful with the and, but we'll talk about that a little bit later. Right now, we're just focusing on the or, which is the addition rule. Okay, so that's going to be the focus of this video. So remember those definitions from the beginning: events, outcomes, simple outcomes. Just make sure you're clear on the difference between simple, not simple, event, outcome. In this case, in this section, we're talking about the events A and B, which may not be simple, right? Calculating the probability of A or B. We've actually done a couple of these already. We'll just sort of formalize that conversation in the context of an addition rule. So here's an example. Experiment. You have a deck of cards. You pull one card at random, right? And we can say, what is the probability that that card is either a heart or a face card? All right, so we have two events, event A and event B, and we're looking for the probability of A or B. Now, when we say A or B, and this is important moving forward before we do any actual problems, A or B means A happens or B happens, or both happen. So this is not an exclusive or. This means either one or the other or both. Right? That all three of these, this one, and this one, fall into the category A or B. Okay, so that's important in terms of our calculations later on. One definition real quick, and this is going to affect how we calculate the probabilities. Events are called mutually exclusive if they cannot happen at the same time, right? Some books use the term mutually exclusive, some books use the term disjoint. They mean the same thing. Mutually exclusive and disjoint, they mean the same thing. What they mean is separate. Did I spell that right? It looks strange. Separate. Mutually exclusive or disjoint means separate. They cannot overlap. They cannot happen at the same time. Okay, so let's do a couple of quick problems I give you two events and you determine if they are indeed mutually exclusive, yes or no. Okay, so problem number one. Event A is you go scuba diving, or a person goes scuba diving. Event B is that person goes skydiving. Are they mutually exclusive, yes or no? The question is, can they happen at the same time? Right? If they cannot, right? If they cannot happen at the same time, then it's a yes. Right? In this case, I think that's a yes. They cannot happen at the same time. Right? You cannot be falling through the sky and underwater at the same moment. It could do one then the other, but with the addition rule, this idea of mutually exclusive, it's like the same instant in time. Okay, next one. Two events. You get stung by a bee, you get stung by a wasp. Are they mutually exclusive, yes or no? Or can they happen at the same time? Well, it's bad luck, but yes, I think a bee and a wasp could both land on you and sting you at the same moment, and that would be a no. Not mutually exclusive because they can coexist. They can happen at the same moment. Event A, find a penny on the sidewalk, find a dollar on the grass. Sure, I think those two things could happen at the same moment. You could look down and see a dollar and a penny at the same time. You pick them up with both hands. Sure, they could happen at the same time. So that's a no. Not mutually exclusive. And so just be careful. It's a little counterintuitive because if the answer is no, they cannot happen at the same time, that means yes, they are mutually exclusive. So mutually exclusive, not and not. Okay, so back to this problem. Pull one card from a standard deck. So you got 52 cards. You got a stack of cards right here. So there's your deck of cards sitting right there. You pick one card at random. What is the probability that that one card is either A or B, right? Is either a heart or a face card? Well, let's see. In this deck, there are 52 cards. So there are 52 possibilities in this experiment. 52 possible simple outcomes from the experiment of pulling a card at random. So it should be something divided by 52. We're using the same definition from the previous section. The definition of probability, you count the number of ways your event could happen divided by the size of the sample space or the total number of ways your experiment could play out. So it should be something, it should be something divided by 52. So now we have to count how many face cards are there, how many hearts are there. Okay. Well, event A, the card being a heart, there are 13 different ways that could happen. Ace of hearts, two of hearts, three of hearts, four of hearts, five, and so on. There's 13 hearts in the deck. And then event B, so let me do this. This is 13 different ways for event A, and if we're looking at event B, there's 12 different ways that could happen because there's 12 face cards. There's 4 jacks, 4 queens, 4 kings, right? So we've counted each, the number of simple ways each event can happen. So 13, 12, would it be 25 over 52? That's the question. I'm pretty sure it's 52 on the bottom because there are 52 cards in the deck. So how many ways could the event play out? 52. How many ways can the experiment play out? It's 52. How many ways can this happen? Is that 25? Well, let's actually look at the deck of cards. Okay, there's the deck. And if you look at the top of the screen, you see the two events. Card is a heart. 13 ways that could happen. Event B, the card is a face card. Well, there's 12 ways that could happen, but visually from this picture, you see these are not mutually exclusive. There's overlap here, right? Those three cards that were circled twice with those yellow bubbles right here, those three cards, they're part of both sets. Those three cards are part of set A, event A, and they're also part of set B or event B. So when you're calculating the probability of an OR, right, two or more things happening at the same time, we're looking at the probability of the first event. That's the 13 hearts out of 52, plus the probability of the second event. That's just the face cards. There are 12 of those, 12 out of 52. Then we got to subtract what we double counted, right? We counted these three cards. The Jack of Hearts is a face card and also a heart. The Queen of Hearts is a face card, also a heart. So we double counted those. There's three cards that were counted twice. Part of the 13 and also part of the 12. So we gotta subtract that. So that's minus the probability of A and B. So it's not 25 out of 52, it's actually 22 out of 52. If you, I mean, you're not always going to have a picture in front of you, but if you just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, you can see there's 22 cards that were identified as part of either A or B or both. Okay, so that's an example of the probability of two events, A or B, when they are not mutually exclusive. There's some overlap there. Now let me go back to an example that we've done already. We did this one in class in the last video. Experiment, roll 2 dice. Okay, so you got 2 6-sided die. There's one there. There's one there. Okay, so you roll 2 dice. And we're looking for what is the probability that you win on your next roll. Okay, so I'm telling you, a win, this is a win. You win if you roll a 7 or an 11, or it doesn't matter, either one. So we're looking for the probability, of A or B. That would be a win. A winning roll is an A or a B. Okay. And this is just a visual aid here. Don't worry about understanding this. This is what the half of the craps table looks like in real life. And the bet we're talking about here is right here on the pass line. It's just all we need to know about this scenario in life, in real life, is that you roll 2 dice. If it's a 7 or 11, it's a winning roll. Otherwise, it's not a winning roll. Okay, so probability of a 7 or an 11. This is the A and this is the B. Well, there's different ways that could happen, so you have to count all the different ways of rolling a 7. So this first die could be a 1 through a 6, and the second die can be a 1 through a 6. So this 7 right here would be a 1 and a 6, a 2 and a 5. This one would be a 3 and a 4. This one a 4 and a 3, 5 and a 2, 6 and a 1. And then down here we got a 5 and a 6. And then this one is a 6 and a 5. So 8 different ways of rolling either a 7. So this would be the probability of just the A happening. right? This would be the probability of just B happening, right? 6 ways to roll a 7 out of 36 rolls, 2 ways to roll an 11, right? So here's event B, here's event A. There's nothing to subtract because there's no overlap, right? So these two events, right, rolling a 7, rolling 11, these are mutually exclusive. And because they are mutually exclusive, they can't happen at the same time. Nothing gets double counted. There's no overlap, so there's nothing to subtract. So 6 over 36 plus 2 over 36 is 8 over 36, and then we have to reduce that fraction to simplified form, 2 over 9. Now keep in mind, like we're getting a fraction from the definition. If you're doing the homework and it says convert, give the answer as a decimal or a percentage, make sure you're converting and rounding correctly. Okay, so we did one example. The first one, pulling a card at random from a deck, 2 events that were not mutually exclusive. Then we did one example, rolling dice, 2 events that are mutually exclusive. And the mutually exclusive part just tells you whether or not you have to subtract something, if something is double counted. So this is the general rule, the addition rule of probability. Probability of the first plus the probability of the second minus the probability that they both happen at the same time. Now, if events A and B are mutually exclusive, then this right here becomes 0. So it disappears. So it's like plus 0. Okay, it's getting a little cluttered on the screen. But that's it. That's basically, this is the, if you Google the addition rule of probability, you will see this. All right, looking good. I think I have one more example to do. So a 2-part example. So if you want to maybe pause the video for a moment and just read the problem, the part in bold, that's the one we're doing first. And then the one that starts if 12% of patients had neither, that's part B. So we'll deal with that one second. Okay, hopefully you had a moment to pause and read the problem. So we're looking for the probability that a patient had either influenza or bronchitis. Okay, so we got 2 events. Event A, right? So the key word here, right, the reason we know this is the addition rule is because we see the word probability and or, right? Those two. Probability or, that's telling us we're using the addition rule of probability, right? We have event A, event B, probability or. Okay. So I just highlighted in red the part of the question that's telling us what we're looking for. Find the probability of A or B. So in this case, they are not mutually exclusive. And we know that because the problem tells us some of those patients had both conditions, the part that's currently highlighted in red, right? This right here is telling us this right here, right? Both can happen at the same time, therefore they are not mutually exclusive. So if we look sort of visually, sometimes it could be presented as like a Venn diagram, right? So I've got, circle A represents all of these patients who had influenza, right? And then circle B represents all of the patients that had bronchitis. But then some of them had both. That's why these two circles are overlapping. So that section in the middle represents the people that had both influenza and bronchitis. That's 18% of the patients. So this 43% of patients had influenza. I'm using red. It's the red circle, right? That 43% is all of this. It includes the blue, right? It's not 43 on the left. It's 43, the entire red circle. So part of that 43 is the 18. And then the 30% that had bronchitis, well, that's everything in here, right? So we see some of those patients were double counted. Some of those patients were part of the 43, but they're also part of the 30. That just means we have to subtract. In the addition rule, we have to subtract. Right? So this is the color coding, based over on the diagram on the left. Those 43% of people are right here, P of A. Those 30% of people or patients is right here. That's P of B. And these 18% that had both, that's the part we're subtracting off. Oh, I'm hoping the color coding is making sense. Okay? So that's 43% for P of A plus the 30% for P of B, looking at them separately, and then minus the 18% P of A and B. All right, so it looks like 55% of patients had either influenza or bronchitis or possibly both. Now, let's move on to the second part of the problem. If 12% of patients had neither, but tested positive for strep throat. So now we're looking at event A, event B, and event, I don't know why that window keeps popping up, and event C. Right? So A, B, and now we have a third event, strep throat. We know these two overlap, influenza and bronchitis. A and B are not mutually exclusive. But C is, because it says in the problem, if 12% of patients had neither, not influenza, not bronchitis, but tested positive for strep throat, right? So those 12%, that's a separate group. So the A and B, we've already done that part, right? That's the 55% from earlier. So visually, the influenza or bronchitis, that's 55% of patients. Right? That's what we calculated in the beginning. The 43 plus the 30 minus the 18. That's always our first result. Strep throat, that circle is off on its own. There's no overlap. Right? Separate, mutually exclusive. So we got 55% in the A or B category, and then 12% in the C category. And the addition rule says we can add them. There's nothing to subtract because there's no overlap. So we're looking at, we're sort of grouping these two together because we've already done that. right? We've already grouped those two together by calculating the 55%, and then adding a mutually exclusive event, strep throat, 12%, total of 67. So 67% of patients had either influenza or bronchitis or strep throat or possibly two of them. Okay, that does it for this video. I hope this was helpful. Addition rule. The important big picture thing here is if we're talking about multiple things happening at the same time, at the same moment, we're using the addition rule. If we're talking about the probability of a sequence of things happening one after another, that's a separate situation where the addition rule does not work, right? So next thing to talk about is the other rule, multiplication rule. Okay, that'll be in the next video.